Hydrogen's potential isn't just in the gas itself, it's also in how we store, transport, and use it. From gases and liquids to solids, hydrogen derivatives unlock its true potential. But with so many options, ammonia, LOHCs, metal hydrides, methanol, and more, how do you make sense of it all? In this episode of Hydrogen A to Z, we are talking D for derivatives. I'll shed some light on the hydrogen derivatives, what they are, how they work, their pros and cons, and why investors and energy professionals need to know this to navigate the hydrogen economy. Let's dive in. First off, what are hydrogen derivatives and why do we need them? Hydrogen is light and has a low volumetric density, which makes it tricky and costly to store and transport in its pure form. That's why derivatives, which are chemical carriers that store and release hydrogen, are game changers. They are optimized for storage, transport, or use as fuels, especially in sectors where hydrogen gas itself is impractical. They allow us to pack more hydrogen into smaller volumes, that is a higher volumetric density, use existing infrastructure like liquid fuel pipelines and storage tanks, and transport hydrogen safely over long distances, including overseas. Store hydrogen long-term without loss, for example, with no boil-off losses like liquid hydrogen. Hydrogen derivatives come mainly in three forms: in gas, liquid, and solid forms. Each has unique technical and economic characteristics. Let's explore each. We start off with the gas hydrogen derivatives. These are derived gases with added transport and use benefits. First off, we look at synthetic methane. This is a combination of hydrogen and captured CO2 to form methane in a process known as methanation. This is used in natural gas grids, heating or power, and the methane yield can be up to 99%. Next, we look at syngas, which is a combination of carbon monoxide and hydrogen. It is an intermediary for many fuels and chemicals, and it's a key feedstock for Fischer-Tropsch e-fuel production. Next, we look at hydrogen blends in natural gas. Hydrogen can be blended in existing pipelines up to 20%, such as in the High Deploy project in the UK. It doesn't require a full system overhaul, but limitations on the materials and appliances that can be used exist. Next, we look at liquid hydrogen derivatives. The first we would look at is ammonia, which is a hydrogen-rich molecule that's liquid at about 10 bar and ambient temperature, making it easier to store and transport than compressed hydrogen gas. Ammonia is already being produced at scale globally. The pros of using ammonia instead of hydrogen is that it's compatible with existing liquid fuel infrastructure. It has a high volumetric hydrogen density and can be directly used as a fuel or cracked back to hydrogen at the point of use. However, the cons are that it's toxic and corrosive, needing careful handling. The dehydrogenation process, which is the process of breaking ammonia down back into hydrogen, is energy intensive and requires expensive catalysts, and purification of hydrogen after ammonia cracking is necessary. For a deeper dive into ammonia, check out the A for ammonia video, which will be linked in the description box. Next, we look at methanol, which is a liquid hydrogen carrier that can be synthesized from hydrogen and CO2, perhaps captured from a CCUS process. Methanol is easy to store and transport, but it requires energy-intensive synthesis and cracking processes. It can be used in shipping as a chemical feedstock and blending into fuels. We have Maersk ordering methanol-fueled ships, and Saudi Arabia and China investing in green methanol. Methanol's versatility makes it a prime candidate for both green shipping and industrial decarbonization. Now let's look at synthetic fuels, otherwise known as e-fuels. This includes synthetic kerosene, gasoline, and diesel, and it is made by combining green hydrogen and CO2 via the Fischer-Tropsch synthesis process. It can be used as part of fuels for planes, trucks, and ships, and is compatible with existing engines and infrastructure. It has lower life cycle emissions than fossil equivalents. The key driver is that sustainable aviation fuels can be used for decarbonizing aviation. Liquid organic hydrogen carriers. These are organic liquids such as dibenzyl toluene that can reversibly absorb and release hydrogen via catalytic hydrogenation, where you add hydrogen, and dehydrogenation, where you release hydrogen. The key advantages of LOHCs are that they are stable liquids at ambient conditions, and so no high pressure or cryogenics are needed. They are compatible with existing liquid fuel infrastructure, so pipelines, trucks, and terminals, and this makes it ideal for hydrogen transport across long distances. There are negligible losses during long-term storage and transport. They are safe and environmentally friendly compared to ammonia and liquid hydrogen. However, there are some challenges. For example, dehydrogenation requires high temperatures and energy input, which impacts efficiency. The catalysts used in hydrogenation and dehydrogenation can deactivate over time, and they can be quite expensive. And as well, still on the subject of cost, the initial cost of liquid organic hydrogen carrier materials and equipment is high. Germany's Chempack Dormagen is the site for the world's largest industrial LOHC plant with a capacity of 1,800 tons of hydrogen per year, showing strong commercial interest. It is scheduled to be commissioned by 2027. Now let's get into the solid hydrogen derivatives. Metal hydrides. Hydrogen is absorbed into metal alloys or pure metals, forming solid compounds, also known as metal hydrides. They can store hydrogen at high volumetric densities by absorption and release it upon heating by desorption. The pros of these are there is high volumetric density suitable for stationary storage. It's a safe and stable storage method at moderate temperatures and pressures. However, there are some disadvantages. The materials are heavy and expensive. There's a slow kinetics of hydrogen absorption and desorption, and the high cost limits large-scale use. Compounds like sodium allanate and lithium borohydride have high hydrogen content by weight, but require extreme temperatures and pressures for hydrogen release and recharge. So how do these derivatives compare? First of all, let's look at the capital costs. LOHC dehydrogenation plants are estimated at about $36 million for 300 tons per day, while ammonia dehydrogenation plants can cost over $500 million for 200 tons per day. Next, energy intensity. Ammonia and methanol synthesis and cracking require more electrical and thermal energy compared to LOHC hydrogenation and dehydrogenation. LOHC hydrogenation is exothermic and releases useful heat, while dehydrogenation is endothermic and needs external heat input. Storage and transport losses. LOHCs have negligible losses during long-term storage and transport. Ammonia and methanol have small boil-off losses. Infrastructure compatibility. LOHCs and ammonia can utilize existing liquid fuel infrastructure, reducing upfront investment. Safety. LOHCs are generally safer than ammonia, which can be toxic. Now let's look at the regulatory and certification landscape. The hydrogen market regulation supports technology neutrality and includes LOHCs as a valid transportation option. LOHC infrastructure benefits from fewer regulatory burdens since it can use existing fuel terminals without third-party access requirements, unlike ammonia. Hydrogen certification is crucial, ensuring hydrogen meets emissions thresholds for renewable or low-carbon hydrogen. Different regions have varying limits, and investors need to trust that the derivatives are made from low-carbon hydrogen. Without proper tracking, grey ammonia and green ammonia look the same on the market. The EU aims for 70% greenhouse gas emission savings compared to fossil fuels, roughly about 3.4 kilograms CO2 equivalent per kilogram of hydrogen, as per the Renewable Energy Directive and Gas Directive. Greenhouse gas emissions from hydrogen derivatives must be calculated along the full supply chain, including storage and transport. LOHCs have specific considerations due to the catalytic reactions and energy inputs. Now let's look at what the future holds. LOHC technology is promising for large-scale long-term hydrogen storage and long-distance transport, especially across oceans, thanks to the high volumetric density, safety, and compatibility with existing infrastructure. Challenges remain around lowering the catalyst costs, improving energy efficiency in hydrogenation and dehydrogenation, and scaling up the industrial plants. The hydrogen market is rapidly evolving. Investment, regulation, and technology advances will determine which derivatives will dominate. Ammonia and methanol remain key options due to existing global markets, but liquid organic hydrogen carriers are gaining ground as a flexible, safe, and scalable solution. Solid hydrides are mostly niche for stationary storage or specialty uses today, pending breakthroughs to lower costs and improve the kinetics. The global demand for green methanol could exceed 500 million tons by 2050. Low emission steel, using green hydrogen is also gaining traction. Hydrogen derivatives are a great way to decarbonize the aviation, shipping, and heavy industry sectors. But there are still challenges: high production costs, lack of hydrogen certification schemes, and policy uncertainty. Still, hydrogen derivatives are becoming core commodities rather than just chemical experiments in the lab. Here's the thing: moving gaseous hydrogen globally is hard, and hydrogen derivatives help to unlock global energy trade. Ammonia has 8 times the volumetric energy density of lithium-ion batteries, and hydrogen derivatives enable exports from low-cost renewable regions to demand centers, and they will help bridge the infrastructure gap while supporting energy security. So whether it's gaseous ammonia, LOHCs, or solid metal hydrides, hydrogen derivatives are the bridge turning hydrogen's potential into reality. For energy professionals and investors, understanding these derivatives, their technology, economics, and regulation is essential to navigating the clean hydrogen future. If you want a deep dive into any of these derivatives, drop a comment below, and don't forget to hit subscribe for more energy transition insights and investor-focused breakdowns. Up next, we have E for electrolysis, how we split water to start the green hydrogen journey. Thank you for watching, and I'll see you in the next episode.